All right, hello there, it's Mr. Collins.
Ms. Cratcher.
And we just want to give you guys an opportunity to kind of make sure that all the information that you tried to assimilate this week got into it. So we're going to start with maybe a new video series, and for lack of better ideas, we're going to call it the formative word, as you see in the nice title. So let's get into it. So here's what we're going to try to accomplish today. You can kind of see it, but it's like 5 big points we wanted to go over with you. Remember, this is purely just make sure that you know what's going on. So let's first talk about the big idea, this definition of similarity. So when you talk about the definition of similarity, you have to understand that this is really just about proving two figures are related by a very particular relationship. And that relationship we're going to call similarity. Now in the end, all that really means is it got bigger or smaller. Okay? So a very, very quick example would be like two triangles. So if I have like triangle A and triangle B, which has now gotten bigger, the exact same shape as a copy. We can say these are similar if they follow two very particular rules. Rule number 1 is that all corresponding angles are congruent. Which should make a lot of sense because if I simply make the object larger, I'm not reshaping it. I'm then making like making a triangle into a square or something. We're just making the angles bigger. The second rule is, and this is the one that's probably the hardest one to actually check, is that all corresponding sides are proportional. Now don't let the word proportional freak you out. There's lots of different ways to say that. We can say that the sides are in the same ratio. Or we can say they're separated by the same K factor. They all mean basically the same thing. Ms. Bratcher?
Okay. So now we need to look at what a dilation is. And a dilation is a similarity transformation. We can prove if two objects are similar through transformations. So, or through dilations. And a dilation is enlarging or reducing a pre-image's size. So, another part that we also need to take into consideration, they're non-rigid motion. So, to give you guys an example, we are going to reduce this pre-image by a K factor of a half. So,
now, Ms. Bratcher, is that 1/2 significant, or are you just kind of picking that out for an example?
I'm just picking it for an example for you guys. So we have M.
It's 3, 1, 2, 4, 5, 6, 7, 8, 9. So 3, 9.
Okay. And then we have N.
6, 0. Negative 3, 0. And 3, 6.
And
So, Ms. Bratcher, can you tell us why you're making a list of your coordinates? Like, what's the point of that?
okay, so I'm trying to organize my work so then we can see how this pre-image transforms to new image. Okay?
But besides only the K factor, is there anything else that we should maybe highlight on this diagram as being really important?
So whenever we're talking about dilations, you can make lines back to the origin, like you guys did in your projects.
And you know, we never really highlighted this like really carefully, but those actually do have a name. Those are typically called the lines of dilation, which implies something really important. That means if you're dilating, it actually is going to restrict your travel to along these lines.
Okay, so after I do this transformation with the K factor of a half, my image should lie on the green line. If we take 3 times a half, we'll get our new one to be 3 halves and 9 halves.
And can you tell us how you're getting that? Like, what'd you do?
So I took 3 times a half.
No, go ahead. And
Okay.
then, so you're just multiplying the vertice by that K factor.
Correct.
And I'm kind of mapping over here while you were giving some coordinates.
And then we also have 3 halves, and then that last one is 3.
this
3.
-3.
Yeah. So I wrote this one. Go ahead. This should be negative. There we go.
Technical difficulties at L. Okay. So
Yep.
if I'm evaluating my previous image, Ms. Basher, can you tell us what I should be looking for? What we should be looking for?
Okay, so now that we have this marked, we need to notice that these lines here are parallel. Okay, so P to, this is L down here, so P to L and P prime to L prime, these two lines that run here are going to be parallel to each other. And then P prime to N prime, and then P to M. All of your lines should run parallel to each other.
Okay. So that's certainly one way we can talk about dilations. Are there others? So you have the lines of dilation.
Yes.
We have the coordinates, which would be a way to tell something dilated. And let's see, what else do we
And
have?
we have the points going back to the origin.
There we go. So if something's been dilated, we can actually tell 3 distinct ways. That's pretty convenient because that tells me that I can prove similarity 3 different ways.
Correct.
Because you just said dilations are a way to prove similarity. Here's 3 ways to prove dilations. That's 3 ways to prove similarity. Yeah, it's pretty important. Now, of course, we're limited to a grid for these, which isn't the greatest thing, but hey, what can you do? All right, let's keep going. What we got next? How do you show similarity? Well, what an ironic question. It's almost like we answered part of that. So it seems like we can show similarity a couple different ways. A few different ways. Number 1, I think you just follow the definition. In other words, you just show those 3 angles, 3 sides. In this case, proportional, of course. Of course, with dilations, right?
Mm-hmm.
So if you can show it's been dilated.
And to show dilation, we need to show 3 different things that we just did.
Which are?
So by making sure that all the points go back to the origin, so the vertices, by your coordinates, and then lines need to be parallel.
Okay. There's a fourth way. Now, if you're watching today early, B sections, not a big deal. You're going to dive into this pretty hard. But if you think about dilations, that's an alternative way to actually follow the definition. Dilations themselves are going to be a shortcut, which means there might be other shortcuts. Look at that color scheme. No. Okay. And we found, or you will find, I should say, that there's only really 3 that make any sense. If you can show in 2 figures, 2 triangles that all the sides that are corresponding are proportional, and even if you don't know anything about the angles, that's enough. On the other end of the spectrum, if you can show in 2 triangles that you have a pair of angles that are congruent, that's enough to assume the side lengths are proportional. And of course, the one that just won't go away, side angle side. So it seems to me we actually have, let's see, let's count them up. We have 1, 2, 3, 4, 5, 6, 7 ways to determine something similar. Pretty impressive. All right. Let's see. Bam.
Okay,
Problem time.
so now we're going to do some problem solving.
And you should note that these, I'm sorry, Ms. Bradford. I'm sorry, you should note that these are carefully picked out to kind of represent the heart of all the problems we had this week.
Okay, so the first thing that I'm going to do is use just the definition of similarity. So I'm going to go ahead and make a list to organize my work to make sure that I'm first checking that all angles are congruent. So we have angle C is congruent to angle T, and then we have angle D is congruent to angle U, and then angle E is congruent to angle B. Wait, yeah, B. Sorry, my U and B look like. So next we're going to make sure that they're proportional, and to set that proportion, we are going to test the different side lengths, right? So the first one that I'm going to do is C to E over
What, DE?
Yeah, DE.
Is there any rhyme or reason to the order you're putting into this?
So I'm making sure that I am corresponding the shortest sides and the shortest sides. So I'm paying attention to the angles that I'm picking and what's side.
Yeah, yeah, no, it also seems like the left, it's always going to be left side over right side as well.
Yes.
Like, so you're always taking like the left side triangle over the right side triangle.
Okay, and then our last one is DC over, actually we should do U. And that would be UT. Okay, so then now I'm going to just go ahead and plug in the values. So we have 12, 9.6, and then we have 5, 4, and then 10, 8. Okay?
Okay, Ms. Brash, I just reduced all those down to decimals, and I can confirm to you those are all 1.25.
1.25.
Indeed.
Okay, so then our next part to this, we're just going to go ahead and write a similarity statement. So then we can say triangle CED is similar. To triangle, it would be TVU. Okay? By a K factor of 1.25.
Now, so now 1.25, and so that's 5/4 roughly. If I were to think that, I keep that fraction. So would that change? Why did you pick that one and not like 4/5? Because we know we can reverse ratios.
Yes. Actually, in this case, it should be 4/5 because we are going from the larger triangle to the smaller triangle.
Okay, so it seems to me, since we don't have like from the beginning, we don't have instructions on which one comes 1st, we can pick which one comes 1st.
Correct. So in this case, instead of writing 1.25, what she said was 5/4. Instead, I'm going to write 4/5. So we should switch this.
Or alternatively, we could just actually switch our congruency statement order, right?
Correct.
Like we can say like TVU to CED.
Correct.
Neat. Okay, so this is like the full definition of similarity. What if we don't have all that? I mean, so let's evaluate this problem. There's something written here, but let's just assume we're saying, well, are these things similar? I think I have a lot of options here, Mr. Brash. I think I have at least two. Like one thing I can notice right away is I have parallel lines. And if I have parallel lines cut by a transversal, I know that certain angles have to be congruent. In this case, alternate interior angles. And using the same parallel line but a different transversal, 3. I have angle 3 and angle 4, and I think that's actually enough. Like I'm not going to use the full definition. I don't think I can because I don't know the top and bottom values. But I can certainly claim like angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 because the alternate interior angle theorem. So these triangles have to be similar by AA. So I can certainly claim, let's see if I A, B, C, similar to C, and NMC, all right? By AA with K equals some number. But in this case, let's see, we have to maybe do a little more work on the ratios. Help me out. Can you tell me what 12 divided by 8 would be? And I'm taking 12 and 8 from right here.
1.5.
Okay, with K equals 1.5. So that's one way to do it. Now, we open the door to having those ratios. So we can certainly show 12 is to 8 in the same way 11.25 is to 7.5. Okay, and if we reduce those back down, those all would just be 1.5. Then, I don't know, what if we take a vertical angle in the middle? So, call that like angle 5 and angle 6. Well, if we know angle 5 is congruent to angle 6, and we have ratios on either side, that's exciting to me. So, I can use the same congruency statement here, but but in this case it would be by side angle side with K equal to 1.5.
Correct.
Which is kind of the beauty of having shortcuts, right? So we have a lot more options than we normally should have. Next.
So in this next problem, we're going to have to set up some ratios to see if this will work. Okay. And the method that I just naturally kind of looked at this problem was just using the side. Okay. So I'm going to use -4 plus 4x over this whole side of 64 equal to 27 over 72, and then that's going to equal 36 over 96. Okay, and then I'm just going to pick some random one. So let's use -4x over 64 equal to 27 over 72, and we're going to use cross multiplication.
So at this point, you're just going to solve for x.
Correct.
So you're taking advantage of the fact that they have to be similar, the ratios have to be the same. You're setting up the solve. Why did you choose 27 over 72?
So I use this side length right here, the JT, as 1, as being 27, and then I had to use this full length right here of J to L for my second one, which was 72.
Why didn't you choose 36 over 96? Could you?
I could have. I just decided to pick one of the two.
Okay, so was this a personal choice?
Yes.
Okay, so now we're just solving, right?
Correct.
I got a calculator here. Let me.
Okay.
So that'd be -288 plus 288x, and that should be equal to 1728. So one more step down, that'll give you 288x is equal to 2016, which when you know it, that makes it 7.
Okay, so now x equals 7. So we can come back up here and plug it in. So -4 plus 4 times 7, which is 28, minus the 4, which is 24, over 64 equals 27 over 72 equals 36 over 96. So now we need to make sure that the ratios are proportional.
I got you on that. They're all 0.375. Right there off the screen, but it is 0.375.
Here.
Okay.
There you go.
So again, we're just using definition, in this case, a shortcut of similarity to actually drive an algebra problem. How interesting is that? Last one. Let's do it. So I'm going to use the same tact. I'm just going to steal Ms. Bratcher's work, basically. And let's just set up some ratios ahead of time. So I have, let's see, 2, which is the small side, over the full side. I think this is where we have to be really careful. This will be 2 plus x plus 1. Should be in the same ratio. X minus 1. More careful than I was just there. Minus 1, okay. Then we have the right-hand side, call it 3. On the small to the right-hand side of the big, 3 plus x plus 1. And finally, bottom small, call it y. Big bottom. 112. All right, so I'm going to use your tactic. I'm just going to kind of selectively pick ratios to solve.
Okay.
But I'm going to ignore the y because it's a different variable anyway, and I'll just grab these two right off the bat. So we have 2 over, and I'll simplify x plus 1. The same over 3, what's that, x plus 4? Yeah. Right. Okay, so some quick cross multiplication yields 2x plus 8 to be the same as 3x plus 3. So kick the 2 over, bring the 3, so x equals 5. Is that right? Check my arithmetic. Never trust math teacher's arithmetic. Trust me. All right, so if we take this 5, kick it back into one of these two x value ratios, I'll just use a blue one. So that'd be 3 over 5, 6, 7, 8. Should see as y over 12. That's a pretty simple ratio.
It should be 3 over 9.
3 over 9, 5, 6, 7, 8, 9. That's an even easier ratio. 3 over 9. Here we go. So we'll see. 36 is equal to 9y. Y is equal to. All right.
We also could have just solve our ratio proportion just by looking at it.
Sure. Yeah. And certainly you can look at like 3 Y's has to be 4, you totally could. All right, so guys, that's a wrap up for the week. That's our whole week in 20 minutes. Not bad since you were in class for like 190, right?
Yes.
So if you have any questions, post them. We'll monitor them. You guys have a good weekend.